Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The fraction 355 over 113 provides an unexpectedly accurate approximation of pi. This numerical relationship, known as the Metius fraction, is remarkably precise, yielding a value accurate to 6 decimal places. It exemplifies the power of mathematical insight, highlighting the contributions of Adriaan Metius, a Dutch mathematician and astronomer active in the late 16th and early 17th centuries. Metius contributed to both pure and applied science. His mathematical work included refining approximations, such as the fraction for pi, and advancing trigonometry. He also made astronomical observations and designed instruments for these studies. This essay examines the life, works, and lasting impact of Adriaan Metius. It explores the problems he addressed, the solutions he proposed, and the enduring influence of his contributions on scientific understanding. The essay emphasizes his problem-solving approach, his ability to integrate existing knowledge, and his capacity to create new tools and methods to advance scientific progress. The history of approximating pi spans centuries, a continuous effort to quantify the relationship between a circle's circumference and its diameter. The ancient Greeks used geometric methods to establish bounds for pi, acknowledging the complexity of precise measurement. Archimedes in the 3rd century before the Common Era calculated an approximation of pi, demonstrating that this constant was between 3 and 10/7 and 3 and 1/7. This early work established a foundation for subsequent investigations, benefiting future mathematicians. Accurately determining pi, a number that extends infinitely, engaged mathematicians across eras, inspiring increasingly refined methods. Metius's era coincided with the scientific revolution, a period of significant intellectual transformation. The established understanding of the natural world underwent radical reevaluation during a time of shifting paradigms. The Aristotelian worldview, which had dominated European thought for centuries, began to yield to a new emphasis on observation, experimentation, and mathematical reasoning. Copernicus's heliocentric model, which placed the sun at the center of the solar system, challenged the geocentric model. Galileo's telescopic observations provided compelling evidence supporting the Copernican view. This era of scientific ferment fostered an environment of innovation, encouraging the scholars to question established doctrines and to seek new explanations for the workings of the cosmos. Metius, working within this context, engaged with these emerging ideas, contributing to the advancement of scientific knowledge. The quest for a more accurate value of pi persisted as a critical problem. The precision of this constant was important for theoretical mathematical purposes and also had practical applications in fields like astronomy, navigation, and engineering. The construction of accurate maps, the calculation of planetary orbits, and the design of sophisticated instruments all relied on a solid understanding of pi. Metius's contribution, the fraction 355 over 113, represented a significant improvement over previous approximations. Its accuracy was sufficient for many practical purposes, making it an indispensable tool for scientists and engineers of the time. This fraction, easily memorized and applied, provided a reliable value for pi, facilitating calculations in a variety of scientific and practical contexts. This essay will examine the details of Metius's mathematical innovations, providing a comprehensive picture of his contributions to this field. It will also explore his astronomical observations, examining how he applied his mathematical skills to the study of the heavens. The goal is to present a nuanced portrait of Metius, highlighting his role as a key figure in the scientific revolution. This study seeks to understand his methods and the importance of his work within its historical setting. It will concentrate on the specific problems he addressed, the inventive solutions he created, and the enduring effect of his contributions on scientific and mathematical understanding. This involves a thorough examination of his published works, alongside an assessment of his influence on later generations of scientists. The exploration will present his accomplishments and examine the intellectual currents that shaped his work, as well as the ways his ideas connected with his contemporaries. The following sections will explore the specifics of Metius's life, tracing his educational background and his academic career. These sections will examine the political and intellectual environment of the Dutch Republic during his lifetime, highlighting the influence of prominent figures like Simon Stevin. The role of universities and scientific societies in promoting intellectual exchange and innovation will be emphasized. The analysis will consider the ways Metius's work reflected the values and priorities of his time, while also exploring how he surpassed the limitations of his era. Adriaan Metius, a figure of considerable intellectual stature, thrived during a period of remarkable transformation in the Dutch Republic. To fully appreciate the importance of his contributions, one must first understand the context of his life, the intellectual currents that shaped his thinking, and the environment in which his ideas took root and flourished. Born in 1571, Adriaan Metius was the son of Adriaan Metius, a man whose own mathematical pursuits provided the young Adriaan with an early and profound exposure to the world of numbers and geometry. This familial influence proved to be a formative element in shaping Metius's intellectual trajectory. Metius, a cartographer and military engineer, instilled in his son a deep appreciation for the practical applications of mathematics a characteristic that would define Metius's approach to his studies and research. Metius received his education at the University of Frankfurt, a relatively new institution that, alongside Leiden University, played a pivotal role in the intellectual life of the northern Netherlands. Universities, at this time, were becoming centers of learning, embracing the burgeoning fields of science and mathematics, and moving beyond theological study. The atmosphere within these institutions encouraged the sharing of ideas and the quest for knowledge. This environment greatly aided the growth of scientific thought, differing from the more fixed scholastic traditions of prior eras. The Dutch Republic, during Metius's life, was a society undergoing swift change. The political scene featured the fight for independence from Spanish rule, a conflict that deeply influenced the nation's character and its goals. The Republic's rise as a major maritime power, along with its growing commercial interests, created a need for practical knowledge, especially in navigation, surveying, and engineering. These needs spurred the growth of mathematics and the sciences as individuals sought solutions to the challenges of exploration, trade, and defense. Simon Stevin, a significant figure in the scientific and engineering circles of the Netherlands, had considerable influence. Stevin, a person of broad knowledge, supported the use of everyday languages in scientific discussion, making knowledge accessible beyond the Latin-speaking elites. His focus on the practical use of mathematics, particularly in hydraulics and fortifications, aligned with the needs of the growing Dutch Republic. Stevin's work, with its emphasis on practical problem solving and its use of decimal notation, helped establish a scientific culture that valued observation, experimentation, and the application of mathematical principles to real-world problems. The intellectual climate of the time was further enhanced by the emergence of scientific societies and academies. These organizations provided spaces for scholars and practitioners to share ideas, research findings, and collaborate on projects. They aided the spread of knowledge and fostered a sense of community among those involved in scientific endeavors. These societies were key in promoting the development of scientific instruments, the improvement of experimental techniques, and the advancement of theoretical understanding. Metius's career developed within this dynamic and stimulating environment. He engaged with the intellectual trends of his era, reflecting the focus on practical mathematics, the value of empirical observation, and the importance of collaboration. The Dutch Republic, a nation seeking independence and economic success, shaped his intellectual growth and provided the setting for understanding his accomplishments. Metius's education, the influence of his father, and the intellectual environment of his time all fostered a mind capable of solving intricate problems. The University of Frankfurt, with its wide range of subjects, provided a basis for his work. The political and economic conditions of the Dutch Republic, with its need for skilled navigators, surveyors, and engineers, spurred his endeavors. The Dutch Republic, formed through war and trade, offered both difficulties and advantages for individuals like Metius. The Republic's emphasis on practicality, its embrace of innovation, and its commitment to intellectual freedom created an environment that supported scientific progress. The expansion of universities and scientific societies, the influence of figures like Simon Stevin, and the demand for practical knowledge created a favorable environment for the advancement of mathematics and the sciences. The intellectual landscape of the late 16th and early 17th centuries was marked by a growing interest in precision, driven by the practical needs of a rapidly expanding world. Navigation, surveying, and engineering all required accurate measurements, and central to many of these calculations was the constant pi, the ratio of a circle's circumference to its diameter. Pi presented a continuing challenge how to determine its value with increasing accuracy. The Greeks, centuries earlier, had addressed this problem, yet it remained a persistent obstacle for mathematicians. Adriaan Metius, using the knowledge of those who came before him and applying his own creativity, made a significant contribution to this ongoing pursuit. Metius's most notable achievement in this area is his remarkably accurate approximation of pi, expressed as the fraction 355 over 113. This fraction, often called the Metius fraction, provides an astonishing level of precision. The decimal representation, approximately 3.1415929, is accurate to 6 decimal places. This level of accuracy improved upon the approximations available then, proving invaluable for practical calculations. Understanding the historical setting of Metius's work on pi is essential to grasp its importance. Before Metius, mathematicians used various methods to approximate pi. Archimedes, for instance, used geometric arguments, inscribing and circumscribing polygons within a circle and then calculating the perimeters of those polygons. As the number of sides in the polygons increased, the perimeters approached the circumference of the circle, allowing Archimedes to establish bounds for pi. His method provided an approximation of pi between 3 1/7 and 3 10^71. This was a significant achievement then, but the method was computationally demanding and the resulting accuracy was limited. Later, the Chinese mathematician Zhu Changzhai in the 5th century calculated pi to be approximately 3.1415926, a value accurate to 7 decimal places, using a similar method involving the perimeters of polygons. He also provided 2 rational approximations, 3.141592 and the fraction 355 over 113, the same value Metius would later popularize in Europe. Zhu Changzhai's work, however, was largely unknown in Europe for centuries. Metius's approach to arriving at the fraction 355 over 113, while not entirely original, demonstrated his understanding of mathematical principles and his ability to synthesize existing knowledge. The fraction can be derived using the method of continued fractions. This method provides a systematic way of approximating real numbers with rational numbers. The continued fraction expansion of pi begins with 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 29 2. Truncating this continued fraction at different points produces a sequence of rational approximations. The initial approximations are 3, 22 over 7, and 333 over 106. The fraction 355 over 113 appears at the subsequent stage of this continued fraction expansion, providing a level of precision superior to its earlier counterparts. The continued fraction method's elegance stems from its efficiency. It facilitates the creation of increasingly precise approximations with a relatively modest computational burden. The fraction 355 over 113, when contrasted with Archimedes' more involved methods, presented a considerable advantage. It delivered a high degree of accuracy with a manageable effort, enabling more precise calculations in practical applications. The practical consequences of an accurate value for pi were substantial. Surveyors, architects, and engineers required the calculation of areas and volumes of circular or cylindrical forms, from constructing buildings and bridges to measuring land. Navigators depended on accurate calculations of distances and positions, where even minor errors in pi could cause significant inaccuracies across extended voyages. The capacity to calculate pi with greater precision directly resulted in enhanced accuracy in these crucial domains. Metius's approximation, while not immediately transforming mathematical practice, was significant. It provided an easily accessible and highly accurate value for pi that could be used in a wide array of calculations. The fraction 355 over 113 became a standard, a demonstration of Metius's mathematical skill and his capacity to integrate existing knowledge into a practical solution. This fraction offered a level of precision adequate for many practical purposes and remained a benchmark for accuracy for a considerable duration. Metius's work on pi is significant, extending beyond the calculation of a numerical value. His contribution emphasizes the importance of precision in scientific and engineering endeavors. His method, built upon established mathematical principles, demonstrated the power of synthesis and the value of finding efficient solutions to practical problems. The fraction 355 over 113 is a reminder of Metius's intellectual legacy, a testament to his ability to contribute to the ongoing quest for knowledge and accuracy. The pursuit of a more precise value for pi, a constant that continues to fascinate mathematicians, drove the development of mathematical methods and their application to the world around us. The synthesis of existing knowledge into practical solutions, as demonstrated by Metius's approximation of pi, characterized his approach. His engagement with trigonometry, a field critical for navigation, surveying, and astronomy, further illustrates this characteristic. The challenges of his era, specifically the need for accurate measurements and calculations, prompted him to delve into this branch of mathematics, leading to valuable contributions in a domain that became indispensable for scientific and practical applications. The core of Metius's trigonometric work centered on the creation and utilization of trigonometric tables. These meticulously constructed tables provided ready access to the values of trigonometric functions for specific angles. The utility of such tables was immense. Surveyors, navigators, and astronomers all required precise calculations of angles and distances. These tables offered a systematic means of obtaining those values, avoiding the cumbersome process of calculating trigonometric functions from scratch each time. The problems of his time were numerous. Accurate navigation at sea depended on a precise determination of a ship's position, which, in turn, relied on the accurate measurement of angles and distances. Surveyors mapped land and created accurate representations of the world. Astronomers sought to understand the motions of celestial bodies, requiring precise data on the positions of stars and planets. Efficient methods for calculating trigonometric functions were essential for these efforts, facilitating progress in exploration, cartography, and our understanding of the cosmos. Metius's solution was elegant and practical. He compiled tables presenting the values of trigonometric functions for various angles. These tables included the sine, cosine, tangent, and cotangent functions, along with their corresponding angles, often at regular intervals. The tables were designed for ease of use, enabling quick and efficient retrieval of values. The content was carefully selected to cover the angles most frequently used in practical applications. The methods Metius used to compute these tables are of considerable interest. The specific details of his computational techniques are sometimes lost to history, but the underlying principles were based on established mathematical methods. These methods involved the use of trigonometric identities and series expansions, allowing for the calculation of trigonometric function values with a high degree of accuracy. Interpolation techniques were likely employed, which were crucial for obtaining values for angles that were not directly listed in the tables. Interpolation, the process of estimating values between known data points, enabled users to derive the required trigonometric values for any angle within the table's range. These trigonometric tables were essential for practical applications. For navigators, the tables were essential for determining a ship's position at sea. Navigators employed instruments such as the astrolabe and quadrant to determine the angles of celestial objects, including the sun and stars, relative to the horizon. Consulting trigonometric tables, they computed their latitude and longitude, facilitating course plotting and hazard avoidance. Surveyors also gained considerable advantage from these tables. They utilized them to measure distances and elevations, thereby generating precise maps and landscape plans. By measuring angles and distances and applying trigonometric functions derived from the tables, they calculated unknown dimensions of land parcels, buildings, and other structures. This was essential for land ownership, construction, and infrastructure development. Astronomers depended on trigonometric tables to analyze the movements of celestial bodies. The tables facilitated the conversion of angular measurements of planetary and stellar positions into distances and other pertinent parameters. Data from these observations refined astronomical models, enhanced understanding of solar system dynamics, and enabled predictions of future celestial object positions. The enduring influence of Metius's tables surpasses their immediate application. They significantly advanced the use of mathematics across diverse fields, encompassing navigation, surveying, astronomy, and engineering. The availability of dependable trigonometric data streamlined calculations, accelerating scientific and technological advancement. The table served as a fundamental tool for scientists and practitioners, empowering them to address complex problems with enhanced precision and speed. Metius's work in trigonometry highlights his commitment to delivering practical solutions to real-world problems. His trigonometric tables, carefully compiled and meticulously structured, represented a substantial contribution to the scientific and engineering communities of his era. They advanced exploration, cartography, and astronomy, leading to further discoveries and innovations. These tables, along with his contributions to other mathematical areas, established his reputation as an influential figure in the scientific revolution. The practical value of Metius's mathematical tables, demonstrating his dedication to applied science, naturally extended into observational astronomy. Within the meticulous recording of celestial movements, Metius showed a keen understanding of the practical requirements for accurate measurement. His work in this field, though sometimes less discussed than his mathematical achievements, reveals a deep appreciation for the complexities of the cosmos and a practical approach to understanding its mysteries. The difficulties in astronomical observation, from the limitations of available instruments to the subtleties of atmospheric distortion, demanded technical skill and a meticulous nature, qualities that Metius possessed in abundance. The core challenge for astronomers during Metius's time was a precise determination of celestial positions and motions. The accepted models of the universe needed accurate data for validation. Imperfections in human vision, the absence of standardized instruments, and the effects of atmospheric refraction all introduced errors into astronomical measurements. Overcoming these obstacles required theoretical understanding and the development and improvement of observational techniques and instrumentation. Metius, a theorist and a practical observer, was well prepared to address these difficulties. Metius's astronomical work used various instruments common at the time, including quadrants, astrolabes, and the telescope, a relatively new invention. Quadrants, simple tools, measure the angular altitude of celestial objects. Astrolabes, more complex devices, allowed for the determination of time, latitude, and the positions of stars. The telescope, a revolutionary instrument, provided unprecedented views of the heavens, revealing details previously unseen. Metius's use of these instruments, combined with his mathematical skill, enabled him to gather important information from his observations. Details concerning Metius's direct innovations in instrument design are few, yet his careful approach to observation indicates a deep understanding of the tool's limitations. It is possible he improved existing designs, perhaps focusing on increasing the accuracy of the scales or improving the setting mechanisms. His knowledge of trigonometry, developed in his tables, was vital for accurately processing observational data, correcting for instrument errors and atmospheric effects. Applying these mathematical principles to astronomical measurements was a key part of his work. Metius's observations covered various celestial occurrences. He carefully monitored the planets' movements, recording their positions against the background of the fixed stars. These observations provided the raw data needed to test and refine astronomical models. He also observed comets, temporary visitors to the solar system that often sparked scientific curiosity and public concern. The appearance of a comet offered a chance to study its path and attempt to understand its nature. Comet observations presented a considerable challenge. Comets, appearing suddenly and moving unpredictably across the sky, contradicted the established order of the celestial sphere. The dominant Aristotelian cosmology, which proposed perfect and unchanging heavens, found it difficult to account for these transient objects. Metius's observations, like those of other astronomers, added to the growing evidence that challenged this view. By carefully mapping the paths of comets, astronomers provided data that helped show these objects moved through the same space as the planets, not in a separate realm. The ongoing refinement of astronomical models relied heavily on the availability of accurate observational data. During Metius's lifetime, the Copernican revolution, which presented a heliocentric model of the solar system, was still gaining acceptance. The Tychonic system, a compromise between geocentric and heliocentric models, was a significant alternative. Precise observations were essential for any model. They enabled the calibration of models, the identification of discrepancies, and the refinement of orbital parameters. The careful collection of data, a characteristic of Metius's astronomical work, directly contributed to this process. Metius's astronomical observations, combined with his mathematical skills, demonstrate his dedication to the scientific method. He understood the importance of empirical data in testing theoretical models. His precise measurements, meticulous record keeping, and rigorous application of mathematical principles enhanced the reliability of his observations. His work contributed to the advancement of astronomical knowledge. It showed how the application of mathematics and the careful use of instruments could reveal the secrets of the cosmos. Details regarding groundbreaking innovations in instrument design may be absent, but the significance of Metius's astronomical work lies in his approach to observation. He utilized the available technological tools, applying his mathematical expertise to extract the maximum value from the data. His observations, though perhaps less celebrated than his mathematical achievements, are a vital component of the scientific legacy. His astronomical work underscores the interconnectedness of mathematics and observation, showing how the two disciplines work together to unravel the mysteries of the universe. His contributions to the scientific revolution are defined by this integrated approach, which combines theoretical understanding with practical application. Adriaan Metius's astronomical pursuits, inseparable from his mathematical endeavors, developed within the dynamic context of cosmological debate. The heliocentric model, advocated by Copernicus, represented a significant departure from the established geocentric view, which had been the dominant astronomical perspective for centuries. The Copernican system, at that time, encountered substantial difficulties, particularly concerning the observed lack of stellar parallax, the apparent shift in position of nearby stars relative to distant ones as the Earth orbits the Sun. This absence, along with the lack of conclusive evidence, fostered skepticism among numerous astronomers. A hybrid model arose in response to this complex situation, offering a compromise between the heliocentric and geocentric perspectives. This system, known as the Tychonic system, after its primary proponent, Tycho provided a framework that attempted to reconcile observational data with existing philosophical and theological frameworks. In the Tychonic system, the Sun and Moon orbit the Earth, while the other planets, Mercury, Venus, Mars, Jupiter, and Saturn, orbit the Sun. This arrangement, while maintaining a stationary Earth, accounted for the observed retrograde motion of the planets, a phenomenon where planets appear to reverse their direction in the sky. The Tychonic system also elegantly explained the lack of observable stellar parallax, since the stars revolved around the Sun. This eliminated the need for an immense, and then implausible, distance to the stars. Metius, engaged with the scientific currents of his era, adopted the Tychonic system. This decision, though perhaps unexpected to contemporary observers accustomed to the eventual success of the heliocentric model, was entirely understandable given the scientific context of the time. For Metius, the Tychonic system provided a persuasive synthesis of observation and theory. It corresponded with the prevailing observational evidence, including the absence of detectable stellar parallax, while preserving the central position of the Earth. Moreover, the Tychonic model possessed a certain elegance, providing a coherent explanation for planetary movements within a framework that was, at least, less conceptually disruptive than the radical heliocentric proposal. The Tychonic system's appeal extended to its compatibility with observational data. It aligned with the scientific methodology of the era, which valued empirical observation and careful data interpretation. A dedicated observer, gathered a large collection of precise astronomical measurements, which supported the Tychonic model. This focus on precision and data-driven reasoning attracted Metius and other astronomers who valued empirical evidence. Metius's adoption of the Tychonic system significantly impacted his astronomical work. He used the framework to organize and interpret his observations, aiming to refine the parameters of planetary orbits and create accurate astronomical tables. His mathematical skills, developed through his work on approximations and trigonometry, were essential. He used these skills to calculate planetary positions, predict eclipses, and build instruments for astronomical observation. The Tychonic system, despite its initial appeal, had limitations. It involved complex motions and did not fully explain some astronomical phenomena. A robust physical mechanism to explain planetary orbits was absent, a problem shared by both the geocentric and Tychonic systems. As observational techniques improved and more precise data became available, the Tychonic system's imperfections became apparent. The eventual discovery of stellar parallax provided evidence supporting the heliocentric model, which weakened the Tychonic framework. The adoption of the Tychonic system, while providing a practical framework for astronomical calculations, influenced how Metius's astronomical contributions were received. His work, valued for its observational accuracy and mathematical rigor, was viewed through the lens of the Tychonic system. His astronomical tables served a specific cosmological framework. As the scientific community adopted the heliocentric model, the practical use of his tables lessened. It is important to understand the context of Metius's astronomical work. He worked during a time of intense scientific debate and evolving cosmological understanding. He chose the Tychonic system, a practical decision reflecting a careful evaluation of the available evidence and the prevailing scientific consensus. His work significantly contributed to astronomy, demonstrating a commitment to empirical observation, mathematical precision, and the pursuit of a coherent understanding of the cosmos. His adoption of the Tychonic system, though eventually surpassed by later developments, highlights the complexity of scientific progress. It exemplifies the process of scientific inquiry, where theories are tested, refined, and sometimes replaced as observations change. Metius's legacy is that of a dedicated scientist, a meticulous observer, and a skilled mathematician who sought to understand the universe's mysteries using the scientific knowledge available to him. Adriaan Metius's contributions, viewed historically, reveal a profound dedication to accuracy and an impressive ability to connect theoretical understanding with practical application. His work's enduring significance lies in both his specific results and his approach to scientific endeavors. His approximation of pi, the ratio of a circle's circumference to its diameter, expressed as 355 divided by 113, remains useful in some engineering approximations. This shows his precision and the lasting practicality of his findings. Consider also the trigonometric tables Metius carefully constructed. These tables, created through laborious calculations and a commitment to numerical accuracy, provided astronomers and navigators with essential tools. The tables enable the precise determination of angles, distances, and celestial positions. They were essential aids in advancing astronomical observation and in the practical tasks of surveying and navigation. They clearly illustrate Metius's dedication to providing usable resources for his contemporaries. His astronomical observations, conducted with the limited instruments of his time, enhanced the scientific knowledge of the era. These observations, meticulously recorded and analyzed, contributed to a growing body of empirical evidence. This evidence was essential in refining cosmological models. His observations added to the accumulating data, challenging established views, and helping to establish a more accurate understanding of the universe. Metius's role in the scientific revolution, a period of profound intellectual transformation, is significant. He was among those scientists who embraced the power of observation, mathematical precision, and the pursuit of a coherent understanding of the cosmos. His work, situated within this dynamic context, reflects the spirit of inquiry that defined this era. He was part of a collective effort to move from the constraints of earlier paradigms and embrace a new way of understanding the natural world. Practical mathematics and astronomy benefited significantly from Metius's efforts. He was a proponent of the practical application of mathematical principles. His work, from his trigonometric tables to his astronomical observations, demonstrated the utility of mathematics in solving real-world problems. This orientation towards practical application helped to accelerate the development of scientific knowledge and its integration into various fields. Accuracy defined Metius's work. His scientific investigations were rigorous, reflecting the standards of his era. His calculations were meticulous, his observations careful, and his pursuit of precision unwavering, establishing a standard for scientific inquiry. This commitment to accuracy is apparent in his mathematical approximations and astronomical observations. He bridged theoretical knowledge and practical application, understanding the importance of both. He integrated theoretical insights with hands-on applications, allowing him to contribute significantly to both. The scientific landscape of his time was changing, and Metius's work left a lasting mark. Subsequent scientists and mathematicians reflect his influence, his focus on accuracy, his contributions to trigonometry and astronomy, and his commitment to practical applications advance scientific knowledge. His work exemplifies the incremental progress of scientific understanding. Scientific progress is a series of incremental advances, each building upon prior work. Metius's contributions represent such an advance. He advanced understanding, furthering a process that yielded a more comprehensive and precise grasp of the world. His enduring impact stems from his dedication as a scientist, his meticulous observation, and his skill as a mathematician. He endeavored to solve the universe's mysteries, operating within the bounds of the scientific knowledge of his time. His contributions, though possibly less celebrated than those of subsequent individuals, are important. They offer valuable insight into the development of scientific thought and the lasting significance of accuracy, precision, and a quest for knowledge. He exemplifies the power of careful observation, rigorous calculation, and the persistent pursuit of a deeper understanding of the natural world. His work reminds us that scientific progress is a collaborative effort, built upon the contributions of many, each contributing to our understanding of the universe. Adriaan Metius, through his commitment and his contributions, earned his place in this continuing narrative of scientific discovery.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.